So today I want to talk about designing a better suspension system or vibration damping system and a couple other things maybe along those lines too, such as better hydraulics or stuff. This is very important for getting a smooth ride for comfort, but also the less you have to replace this, the better for the environment in many ways, so more environmentally friendly. It has to do with energy efficiency of cars and more, especially bumpy roads, robotics, and much, much, much more. So, what are kind of the modern day suspension systems? Well, you can have a efficient suspension system where you just have a wheel attached to one spring. This isn't the most efficient use of energy, or a wheel put onto any type of dampener, because let's say one wheel needs to go up, another wheel needs to go down at the same time. So it's like one's going up a bump, the front one's going up, this one's going down a thing. Well, the force that's moving this wheel up isn't going to the other wheel to move it down. This means that it's more disleveled, the whole car, more easily. It also wastes energy because energy is put into forcing this wheel up and this wheel down instead of energy going from this wheel that's pushing it up, going this wheel to push it down. So if you have a suspension like the rocker system, which I'll just quickly show one rocker system here. This is a simple one where with six wheels, but I'm only showing three, where this wheel can go up, forcing this wheel to go down, or when this wheel goes up, both of these wheels go down, kind of like on a lever, but you have mobile levels going on, like I drew in a diagram, so it all balances out. Much more efficient, and it's more efficient than usually, it's also smoother ride. It's more efficient than usually recovering energy from brakes or dampeners, which you can do like regenerative braking, this regenerative cycles with the bumps, but you do lose some energy compared to a smooth, perfectly flat road. Now, does the system always work? No. You have to have the bumps lined up just right, but you can usually get a very, very high savings of over 50%. Now, I just drew a solid one, and the solid ones have been used for a long time, and they've been used in such places as Mars and stuff, but they have a couple disadvantages, and that leads to alternative hydraulic ones. Now let's talk about hydraulic ones. Well, hydraulic ones, what it does is there's a fluid. Instead, when one wheel pushes up, this fluid goes along a pipe and pushes the other wheel down, if it has less. Now, if both wheels go push up, the whole system moves up as one big surface smoothly. So it keeps a very smooth platform. You also have your counterpart pneumatic. And pneumatic systems, what they do instead is pneumatic that uses air. Hydraulics uses liquid, pneumatic uses air, and there's some weird ones in between. They have a lot of advantages. With hydraulic systems, you can have every single wheel easily, without thinking about too much about how it's done, connected to each other with using these pipes. In which lets you have a lot more input and control and flexibility than you have with the solid state. Solid state, like I showed here, you have to really think about the design, how everything is attached to each other. Everything is attached to each other in very certain ways, and there's a limit to how much wheels you can directly transfer to other wheels. Another one is that with these systems, you can put complex valves to give it kind of like pressure relief valves. If it gets really pressed really hard, there's a relief valve to lower pressure, so the whole thing can handle really big bumps really fast when there's really big bumps occurring, or when it's driving really fast. When it suddenly knocks in, there's a lot of pressure. And you can have other valves for like more complex logic, or to prevent or make some wheels go up faster than other wheels because the fluid flows more easily there. And that can give you complex control when you might care more about the front being stabilized than the back, because maybe the front has is where the power is coming from, because you have your engine in the front. So if the front gets lifted off the ground, it's worse. So you keep that one pressed more against the ground. You can do that with complex control valves. Another thing you could do beyond that is, compared to the solid one, is you can make this whole thing a ton, and I really do mean a ton, more compact, because you don't have to have all these big levers that are moving all about and stuff like that. And these levers could get stuck if they're exposed to outside, so you need suddenly a bigger vehicle and everything. Another thing that can be done with this whole system is that with hydraulics, is that you can have sound dampening by having the hydraulics use fluids that move in different ways, that they kind of slush around when you shake them, and that slowly absorbs the sound. When a solid, sound travels really well through it and doesn't get absorbed as much. And whenever sound hits two different interfaces, some of it gets absorbed, some of it gets reflected, and some of it cancels out. Because it's like, what happens is that a couple things, some of it is slowed down, and when it slows down, it bends. Because it's like, if you're walking at an angle into a muddy patch, the thing that hits the mud first slows down more, and that causes you to curve into the mud. But some of that sound wave actually curves right back away from it and spreads out more, causing it to lose energy. Some of it curves back and cancels in on itself. Another thing is that sound in liquids travels differently in solids. Solids, it travels very much more for crystals, from one thing bumping into another thing. And sound can also spread out more in other directions, because liquids can spread out stuff. When in a solid, sound travels, in a liquid solid, it's much more individual molecules traveling a far distance. And also individual molecules can hit another molecule and spreads out more in a perpendicular direction. When solid, it's much more molecules or whole crystals vibrating together and hitting each other, which causes, when sound travels in different modes between different things, it bounces back and stuff and spreads out more. Also, they vibrate at different frequencies oftentimes, and that can cause cancellation, because if something is vibrating 2 times faster, half the time it's going to be in a mode that it cancels out, like right here. So you have all those things that hydraulics help get rid of sound, and with also sound traveling in the pipe and bending in different ways, because sound travels in fluids much more in just one direction, while in pipes it will just bend around it. So you have it traveling different directions and maybe canceling out more that way. So beyond all that stuff going on, there are definite advantages of having a solid for your device. Now here is the advantages of having a solid. Solids have, in a solid device, you never have to worry about it leaking fluids or anything like that. In a solid device, because there's less friction in the fluid, and also how sound travels through it, it oftentimes heats up less. Also, the transfer of energy is actually more efficient and fast. You can see this if I have a solid pole and I push with it, it's a very quick transfer of energy, and almost all the energy from one end goes into you. If I instead push a liquid through a pipe at you, some of that liquid slows down to the friction in the pipe. Some of it doesn't. This becomes to pressurize the liquid, and you lose that energy. It just also, the more extreme case would be air, where if I try to push you with a balloon, some of the energy you can see just goes into flattening out the balloon. And some of it also takes a little longer to push you. So this is more fast and efficient transfer of energy, which is something desirable in all these systems, it's more predictable. With hydraulics, to some extent, you always have to do fluid dynamics and simulations and stuff like that, because you might get sound waves, you might get turbulence, you might get weird things. If you shake up a solid in a bouncy ball in a container, you can very predictably see how the ball bounces in a container. If you put a liquid and don't fool the thing up, you can see the liquid splashing around and it's chaos. Now, when a liquid is contained nicely in a tube, it does become more predictable. But still, it's not the same extent as a solid, which is my main point here. Another huge advantage is it's more directional, which I kind of briefly already stated a little bit. And by more directional, what I mean is that this is transferring force in this rocker-based system. You know exactly how it's transferring force in one direction. Well, in a fluid, it can some of the energy goes pushing outwards on the side walls, which can slowly damage the system and stuff like that. And it also causes all the other problems, like making it less predictable, losing energy while it's traveling, making it less fast. But that's just one subcategory that affects more than subcategory. It also affects wear in the pipes and stuff like that, and the whole system. A huge advantage is it's less environmentally dependent. And by that I mean, all these systems, a liquid behaves very differently at different temperatures, much more than a solid. Everything behaves differently at different temperatures, but liquid expands much more in temperature. Compare a thermometer to and compared to also just look at water when you're boiling it, stuff. Liquid also changes its viscosity much more at temperature, so that's how thick it is and how easy it flows. A liquid can break down at high temperatures, it can freeze, it can turn into gas, it can have so much more. And in the extreme conditions, this is a big deal. This is partly the reasons why the rovers on Mars do not use liquids. They use this rocker baby system that I drew down here, is because of this highly dependent nature, and that steel is more reliable in so many ways than trying to design a pneumatic system in Mars that might leak or get punctured or damaged also during space flight. It's dependent on pressure, outside pressure, so much more. The fluids could decay slowly. Some fluids are amazingly stable, some are not. Beyond that, I want to also say a couple of things I missed is it's easier to repair a solid system. Just switch out a bar or something, or you can even bend it back in shape. Then a hydraulic system, where you have all the leaks and stuff, the hydraulic system, the leaking fluid could cause damage into the system. Beyond it causing damage to leaking fluids, the leaking fluids could, in theory, now this is all in theory, could also just make the whole thing not work. When a little nick in here, the system could still work. You can possibly overcome some problems with the solid by making this whole thing a little bit bendable, not bendable, foldable, and then you fold it out when you have another planet or something, if you're landing a rover, but that doesn't work very well for cars. And you can have hybrid systems, but hybrid systems do not work as well, because what the problem with hybrid systems, simply put, is that you end up losing some ability in either one, and it doesn't perfectly compensate. If I put fluids, how do I put a fluid in this whole system while making this joint easily turnable? It's a lot harder than you think, and you can't figure out a possible solution, but it's hard to have a turnable joint like a lever and have it also be a joint where a fluid travels through, and you get vortices oftentimes with the fluids, more friction loss with the fluids and stuff like that, and your lever doesn't work as well. So I think I've come up with a possible solution to this. It doesn't do everything. In certain cases, it'll outperform both in its best scenario, but sometimes solid will work better. Sometimes hydraulics will work better. Sometimes it can do everything a solid can. Sometimes it can do everything a hydraulic can. Sometimes it can. And it has certain also advances that just always will be better than this system. So let me explain my system. Instead of having a fluid, you can have either this with a fluid or no fluid, depending on the system you're designing. But you have a pipe filled with a bunch of small sphere-like particles that could be all touching, or there could be little gaps in between, but it's going to be a big gap in between. And these little spheres can be hollow or not, and I'll get to advantages of different designs, help transfer the load from one place to another place by being compressed or moving. So much like a hydraulic system has, where you press them and this whole thing kind of flows and pushes on a thing. But because these spheres are solid in this part, they can behave more like a solid thing that can be more directional than a liquid. So you get the faster transfer of weight. Not only that, we can make it so that if this whole thing gets, let's look at that, so you have the more directional part of a solid, maybe not always perfect, but you can have more. You have the more compact thing, and you can have more complex control valves, even though depending on how well you make the spheres flow is depending on how well the flow valves are. And you can get different, the smaller the little solids are, the better. That depends on the shape, of course. It depends on how much liquid, or do you have liquid compared to ones, how tightly packed. So, but you can get possibly the complex control valves. You can have as many outlets and inputs as you want, even though, again, it's probably not going to always be as good as hydraulics. In some cases it will. Definitely more compact. You get some of the sound dampening of fluids being able to sound dampen, and you will get more, and I'll get to that. You could get leaks. However, solids do move out of leaks slower than non-solids, and that would help keep it in. Now, I'm going to get into ways we can even do it better. You get less heat in a liquid with vortices and stuff forming. You might get some more rubbing in some cases, like generally see. In some cases not, depends on the particles and a lot of other factors. But there's a way you can help with heat even more with this, which I'll get to again. You get partially the effects of faster, and sometimes you will get faster. It's more predictable than a hydraulic system, and sometimes it's going to be even more predictable than a solid, and I get that. It's less environmentally dependent, definitely, because we can make it also more suitable for different environments by switching out different components, which I'll get to, but it's definitely part of it's solid, so not all of it's going to have that temperature expansion or something like that, and there's also more empty space for it to expand or contract. Now, what are the very specific advances of the system? Well, having a bunch of small spheres like this could be a lot better at dampening vibrations. The reason why is every time it hits a sphere, remember again, it's like every time it hits a sphere, it's like it hits a different interface from solid to liquid, or solid to gas, or solid to another solid but not the same solid, to solid to empty space. So every time it's going to scatter the sound, every time it scatters the sound, some of the sound can and will get canceled out, dampening the vibrations. You also can have it a little bit move around and spin a little bit or something to dampen vibration. Also, vibrations do not travel neatly through a sphere. A sphere curves, so if a sound hits here, some of the sound is going to bend around the sphere and kind of get trapped or lose energy bending around the sphere and actually bend and interfere with itself. This is a well-known phenomenon. If a sound hits it, it's going to scatter more because it hits the sphere, and that sphere almost acts like a lens that focuses and unfocuses sound, scattering and canceling it out more and spreading out more. just like how little droplets can sweat out light waves and cause rainbows. And it can also spreads out different frequencies of vibrations differently, causing even more cancellation and causing the whole thing to have more even noise. So bigger vibrations go in one direction enough, which can be used to design systems to dampen sound even more by causing low frequencies to more interact with low frequencies and high with high. But that's engineering is more complicated. Damping out the sounds and such can also help reduce heat caused by sound. And it can also do other really, really cool things, such as redirect some of the sound energy more into a system that actually turns into energy. And you can use spheres very efficient, with piezoelectric effect or other things, or triboelectric effects like this to generate electricity. Piezoelectric effect turns sound and pressure waves into energy using materials. Triboelectric turns friction. You can only get a little bit of energy back, but over a long time it might be significant, and it will help also further decrease any vibrations that negatively affect the system and lead to wear and tear. Another thing that I want to point out is it can help cool the whole system down. Now, the way it could help cool the whole system down, and this is, in my opinion, very interesting, is that there is more solid here, and solids conduct heat faster than liquids usually. Not always, usually. So that's better than a hydraulic system with conducting heat, and you can also argue that in a hydraulic system less heat is generated in the first place in certain instances. But not only that, is sometimes a mixture of liquids and metals in some cases can conduct heat faster than liquid or metal alone, because liquids can conduct heat through convection and along the convection, and also phase changes from liquid to gas or liquid to solid. Phase changes will be more complicated to design, but convection is a real thing. And convection is these little currents that's from hot to cold. Now, a big current, you have a lot of stuff in the middle of the current that's not actually transferring that much heat. But a little current, or a very thin one where there's not a lot of middle thing, you don't have the middle loss, you have just the big current getting heat, and that can make it more efficient. Also, you can have more efficient, and it's only on the surface of the particles, so you get less of these big currents and more of these smooth ones, destroying it. Another way, also heat on the surface of liquids is conducted more fast, and everything touching the solid will be a surface of a liquid, and that's because heat is most efficiently travels along the surface of a liquid. And I'm trying to figure out a good explanation, but imagine that, let's see, liquid surface. Here they show it, but on the surface of liquid, you don't have it traveling up and stuff much more, so you have it more traveling this direction, so speed increases in this way. You can also use it to recover energy using something called a thermoelectric property. And the thermoelectric property, what the thermoelectric property does is it takes heat and turns into electricity by making heat not conduct as well in one direction as electricity. So electricity becomes more the way that energy is conducted. That's a very rough approximation of what actually goes on, which is a lot more complicated. But some of the best thermoelectric devices combine solid and liquids. It's not the most efficient, but it will help cool down the system and give you a little bit of energy back. Another very, very cool option would be to make this whole thing self-healing. Now, how would we make this whole thing self-healing? Well, you could make this whole thing have either that when it spills, it could stick to the side walls, but it only sticks to the side walls when it's cut because there's a little thing here that's sticky on the outside. Then it could stick the little particles and it could slowly form a barrier much faster than the liquid could. Also, if it's leaks, some of the energy is also going to still be transferred this way for a while, and along too because of this momentum, unlike liquid, so it's going to pour out less fast. You could also have a puncture cause stuff to clog up with more advanced things, like when you cut yourself, your blood clots, by having stuff at the puncture site spill out its contents of the balls, and that can cause stuff to agglomerate and polymerize and in other ways become more of a solid. Or you could have something here start chain reaction, slowly make a clog and stuff like that over time. This whole thing, beyond that, this whole thing is much more tunable. And by tunable, what I specifically mean is that there's much more components in it, so you can tune it by having different types of particles in this whole things, which you could do different size particles, which could disperse sound in different ways. You could have ones that are thermoelectric and piezo, and different types of particles with different ways of recovering energy. You can change the particle size, change the flow characteristics. You can add a carrier fluid, not only solids, to change this one. You can change the packing density. There's a lot more things you can play with to make this whole system work in different ways. But beyond all the things you can play with to make this system work in different ways, is you could, in theory, and I'm just saying in theory, you could take all this and you could have different things at different points. So you could have bigger balls over here or more squishy balls over here, and so on and so on. So you could change the properties as you go throughout the material to more transfer, to actually make up for not having as complex valve system or as good valve system, but even give more tunable than a hydraulic system. However, it slowly might mix depending on how well particles from here can travel to there. A way I just thought about making this whole system even better, and I just thought about that, is you could line up these particles with like a magnet-electric field. So instead of having balls, you could have long spikes that travel even more efficiently with energy in one way, or you could stretch them out in that way. That way you could get even more advances of a solid or something in this system without being a solid. And particles will contain more in the place. You can also tune its properties, because there's a lot of materials that are solid that can change how hard or not hard they are, or change how viscous they are with liquids and stuff, or with magnets, electricity, and more. So you could tune it that you could use a magnet to increase the vibrational resistance, so I make it more spongy and floppy, or make it more hard for different terrains and stuff like that. Another thing you could do is invent this whole system to have better anisotropic properties. So what is anisotropic? So anisotropic is how much something, so anisotropic is a big word, but isotropic means everything is the same in every direction. Like density of a material is always the same in every direction for most materials. And for not every direction, also spatially. So every location material has the same density, or it's the same material throughout the whole thing. Anisotropic means depending on your location or direction, it changes. Now, by varying the material, you could do that with here, which could lead to vibrations traveling in very specific directions, or you could have it contain vibrations better. And you could do it with heat travels much more fast in one direction than another direction. So you could control the heat transfer for better cooling, or you could use heating, or so much more. We've already talked about it for making complex logic for how the wheels work. Another thing you could do with anisotropic that would be very useful is that you could, in theory, and all the magnetic and electrical alignment could help with that, is you could even make stuff like with invisibility cloaks, and people have made invisible cloaks with sound waves, and that means that the sound wave that hits in the middle of the invisible cloak when you're inside actually bounces back and hits you in the back, and sound doesn't travel into it. So that could stop vibrations from going into the wheels, because it just goes around the bar here and out the other end, such as the bar never existed. You can look up sound wave invisibility waves and look up scatter cancellation for much more complete, or transform. Scatter cancellation uses how it scatters off stuff, and transformation looks more at like how fast it travels through stuff as a rough separation of the two different fields. Another thing you could do is, unlike the solid one as much, is you could have this technology be in the wheels, which most wheels are not very good at capturing back the energy they put back that they absorb from vibration stuff. But this could make it better at capturing the vibration by transferring it to a different part of the wheel, which could mean the wheel hugs the surface better. And when the wheel hugs the surface better, but deforms better, it would help conserve a lot of energy, because it also increase friction across the surface in a positive manner. Think about friction then as grip on the surface, while reducing friction over here. So it could make a much more energy efficient wheel. And in some vehicles, 5 to 20% of energy lost in the vehicle, I believe, is lost through the wheels. So this could be a really huge advantage, and it could lower wear and tear on the wheels. Another thing you can do with this whole system is this is a perfect system to make highly non-Newtonian. So, roughly, what is Newtonian? Well, Newtonian means that the viscosity roughly varies linear with the pressure applied or force applied. What that means is that when you hit water, you feel it pushing more against you when you're going to travel faster through the water. Water is a pretty Newtonian, not fluid. Same as with oil and stuff like that. You feel it more when you're doing it, and that's because it starts to build up and get pressurized. But there are some materials that do not follow it. They get a lot harder, a lot faster. And viscous is like how easy material flows around something. An example of something that is positively, I think I believe positive, I always get confused positively, but I think that gets a lot harder, a lot faster. It's a mixture of cornstarch and water. With cornstarch and water, the cornstarch particles, if you hit it really fast, bump into each other more and don't have time to slide around it with the water, and becomes almost like a solid. There's a couple other ones like that if you hit it hard, it becomes it. Now, nothing is perfectly Newtonian either, but there's also things that if you put pressure on it, that they become less viscous. And an example of that is shampoo, also ketchup in some situations, not in every situation, but sometimes ketchup. And the reason why is that they have molecules that are usually long and tangled, but when you put force, molecules slip past each other and can't get and untangle, and then the whole thing can flow more easily. That's a simple explanation of it. You also have non-Newtonian fluids that have some sort of memory. So like they remember the last time you hit them, and they take a while to become softer, or if you hit them multiple times, they become harder and harder on each impact, or the reverse softer. There's things that become act differently, really weird with shear force, which is force in different directions. So like one is going up and one force is going down, and they become harder or less hard, and that usually has to do faster than you would expect. And that usually has to do with how the molecules on a molecular level entangle each other. But anyways, with this system, you can make this whole system highly non-Newtonian. And what I mean by that is that everything can move in such unique ways and compress that it doesn't follow these Newtonian dynamics, and you can choose your dynamics, which might be very useful, because there might be a point that you don't want it to flow, that you want the whole thing to act as a solid, and the whole thing just bounces up and down because this is too much stress on the system. Or you might want to get it really hard and strong when it hits a big impact. Or you might want it where it's just kind of flopping loopy because you just want it to react really fast to a hole and have the whole thing go down the hole. I don't know as much for that one case, but you can understand that sometimes a highly non-Newtonian thing might actually be desirable. Now, you can also design this whole system with different types of spheres. And what I mean by different types of spheres is that you can have spheres that are easy, or other things that are hollow inside and have certain properties to save on weight or mass, or to make them more squishy so they act more like a fluid without there being a fluid. You can have them completely solid. You can have the spheres have anisotropic properties by making them out of rings or different materials at different ways. Rings can move more easily in this way, but they don't compress, but they compress more easily along the ring. So you can see on the different structures. You could also have a system that I like, which would be a circle with a couple holes in it, or that's partially porous, but roughly it always stands as a circle, but it fills up with liquid, and if you squeeze it real hard, the liquid gets ejected. But when it unsqueezes, the liquid can get back sucked into this whole thing. That way it can refill or unfill, and so you can have more of these things in it. And you can also make it more highly non-Newtonian, and just put this whole thing together. Well, thank you for listening. Please like and subscribe. It really helps the channel out. I'm trying to reach 1,000 subscribers in a year and 4,000 watch hours, which is really hard, but with your help, I think I can do it. Also, if you have any ideas for future videos, comments, or suggestions, please leave them in the comment section below. Thank you again very much. Goodbye.